This conference will now be recorded.
Hello, everyone. Good morning and good evening, depending on where you are located now. First of all, I would like to thank GTT-Technologies for arranging this meeting and giving us the opportunity to present some of our data using the FactSage software that we published using this software. So in this presentation, regarding my affiliation, you can see it on the screen. My name is Mohammed Al Harahsheh. I'm from Jordan University of Science and Technology. And in this work, I have a collaborator, Professor Mohammed Noor Al Tarauna. He is now located at United Arab Emirates University in United Arab Emirates. So I will talk about the thermodynamic analysis on the oxidative pyrolytic treatment of electric arc furnace dust and tetrabromobisphenol blend. My talk outline will contain the following: background information about the dust and the plastic waste in general, especially brominated flame retardant. Then I will present the main aims and objectives of this work. I will show some of our previous publications, those concerned the use of FactSage and others related to the electric arc furnace dust. Then we will talk about the dust characterization experimentally that we did for and were essential for doing the thermodynamic analysis. Then I will talk about the thermodynamic analysis and the approach that we followed. Then some of the main results, and finally the conclusions. So electric arc furnace dust is particulate material produced as waste byproducts during the smelting of steel in electric arc furnaces. Okay, there we use recycled scraps, galvanized steel, etc. All waste steel and iron byproducts. This dust is very fine matter. It is classified as environmentally hazardous waste, and it contains high concentrations of heavy metals like zinc, cadmium, lead, manganese, etc., in addition to the high content of the iron. Okay, normally the particle size or large proportion of the particle size of this dust is less than 10 micrometer. It's generated in a huge amount, 15 to 20 kilogram of dust per 1 ton of molten metal, and therefore a huge amount is accumulated worldwide, like 5 to 7 million tons yearly is accumulated worldwide. And one distinctive feature of this dust, it contains high zinc content in the forms of zincite, zinc oxide, and franklinite. Which makes it a valuable waste material. In addition, it contains lead in good proportions, as you will see later. So what they normally do with this dust, for the extraction of zinc because of high content, either they go hydrometallurgically or pyrometallurgically. Hydrometallurgical may be alkaline or acidic leaching. Alkaline leaching suffers from slow kinetics, while acidic leaching suffers from the poor selectivity during the leaching of zinc and lead. For pyrometallurgical operations, the only well-established technology is the wireless process, which is based on carbothermic reduction of the dust to produce zinc oxide, zinc and then zinc oxide. So the new approach is to combine this dust with the plastic waste, these that are halogenated like PVC or flame retardant materials. So again, huge amount of plastic wastes are accumulated worldwide, and they are piled everywhere. Either they are incinerated or they are piled in the landfills, and a lot of problems generated from this waste accumulation. One possible route for treatment of the plastic waste is to do pyrolysis, incineration. During this process, we heat the plastic material, and when we talk about the brominated flame retardants, especially the main component, which is tetrabromobisphenol, HBr is released plus organic materials. And these materials are highly toxic. HBr cause acidity and corrosion for everything, material of construction of units and everything. So the way to minimize HBr release is to add catalysts like metal oxides. In this case, you will form metal bromides. Like zinc oxides, we add cadmium oxides, lead oxides. These, fortunately, are the main components of electric arc furnace dusts. So the aim here is to combine these two ways together and do pyrolysis. Now you can do pyrolysis to high temperature, where you can vaporize these bromides or chlorides, or you do intermediate temperature treatment, and then you do conventional hydrometallurgical operation, i.e. leaching. Okay, and we aim using FactSage to model this system and see what will happen. Okay, just before I start my work, I just want to mention like 4 papers that already published in the past 2 years, where we talk about electric arc furnace dust and also using FactSage. So what I'm presenting here is only small part of the benefits of FactSage that we highly value. Okay, these are another 2 papers, and this is part, it is really not updated list of the publications that we already have published on electric arc furnace dust treatment with the plastic materials. So to do the analysis using FactSage, we need data. So we did characterization for the dust, XRD, to find the mineral composition. So we found it contains a lot of zinc oxide, franklinite, magnetite, sodium chloride, potassium chloride, also iron in the form of hematite, lead in the form of lead oxychloride, etc. Now, as you notice here, we have sodium chloride and potassium chloride. So we, in our modeling work, we did 2 things. We first assumed that it is present, and secondly, we assumed that we washed this dust to remove these chlorides, because they are highly soluble, and see if there are any difference on the impact of their existence in the dust during the treatment with the plastic materials. Okay, we did chemical analysis, so we digested one sample or several samples and took the average. And as you see from the chemical composition, we have in a real sample collected from Jordan, very high concentration of zinc, certainly high concentration of iron, lead in good quantities, and also you can see cadmium, which is very, very toxic elements, in addition to the other elements that you can see in this table. So additionally, we did total carbon and total inorganic carbon, and we calculated that we have in this dust about 1% of carbonates and 2.5% of free carbon. Okay, now coming to the thermodynamic analysis, our approach was like follows. So we use the equilibrium module in the fact stage, which implements the free Gibbs enthalpy minimization method. And we assume that we have a constant mass of 100 grams of the dust with the chemical composition that we showed. This composition, we converted it to it's not seen here, it's not shown here really, to a mineral composition or compound composition. Then we took the following scenario. We mixed this dust with different proportions of the tetrabrom bisphenol, and here we use the TGA analysis of pure tetrabrom bisphenol and calculated how much we had HBr released from this material and how much residual material remains after the pyrolytic treatment, which I think came to about 20%, which is normally backbone carbonaceous materials. Okay, and we use the amount of the HBr here and put it in the software to react with the electric arc furnace dust components. In some cases, we added oxygen, and the amount of oxygen added was equivalent to the amount of carbon in the dust and the amount of iron or ferrous oxide present in the dust. Any species from the calculation with mass less than 0.1 were ignored. We started with the initial temperature of 200 degrees, knowing that the tetrabrom bisphenol decomposition temperature is 280, but really we started with this temperature to see what will happen. Okay, sorry, this is the mineral composition of the dust. We had several assumptions. For the interested people, you can find them in one of the papers that already published in this topic. So here we looked at, and I see I'm running out of the time very quickly. We took these three proportions or three mixtures and looked at several species, mainly zinc species, lead species, and iron species. We looked at them using this software when the environment is inert, so no oxygen. Then we looked at them when the environment is oxidative in presence of oxygen, but not washed, oxidative condition, washed dust, and finally showing the recovery of the species. And here we can see an example. Here the inert conditions, we can see that this data is collected from the software. As a function of temperature, we vary the temperature from 200 to 1000 degrees, and we can follow several species that are formed during this treatment. We can see here zinc bromide solid, which is become liquid here, then become vapor here, okay, and other species as seen in this slide, okay. Now, what happened when we introduced the oxygen? Okay, this is, by the way, unwashed dust. When we introduced the oxygen, we noticed that some of the zinc became as zinc iron oxide. Okay, in addition, we had zinc bromide gas, solid, liquid, and gas, and some other species that are coming from the components. Okay, then after we washed the dust, we looked in absence of sodium and potassium chloride and noticed the profile, and we here see the recovery of zinc in gaseous phase, irrespective it is zinc bromide or it is zinc chloride or complex chloride like this compound. Okay, so we see here not good recovery unless we go to the inert conditions, very high temperature, we can get the high recovery. Okay, This is overall recovery. The same thing we did with iron, okay, and we see under inert conditions, we have high concentration of iron coming as gaseous material at high temperatures, okay. Now with regard of lead, we have the same profile, and finally we look at the recovery. At these conditions, lead recovery was very good, especially under oxidative unwashed and oxidative wash dust. Under inert conditions, here we had some reduction reaction that formed some compounds and dropped the amount of gaseous lead bromide. Okay, we here is the summary of the recovery of these elements. Now I want to go and jump the same we did for the 1.5 ratio. Okay, and I want quickly to jump to this graph, okay, which summarizes the recovery of these metals. Here we see when we had more of the plastic material, more bromination occurred, and we achieved high recovery of zinc under oxidative conditions, okay, while it is under inert conditions, occurs at higher temperature, and the recovery did not reach 100%. The same occurred for lead, okay, under oxidative conditions, especially when you see this red line. But what is extremely important was for us is the selective depression of iron release when we added oxygen to the system. So we see all iron became iron oxides in the form of hematite. So this fascinating result that we reached from the fact stage, we applied it really. We did it for brominated flame retardants, and also for the PVC when it is mixed with electric arc furnace dust. And there we found really fascinating data that we went to the lab and did the experiments, and it came, luckily, the data very comparable to those calculated using the fact stage. Okay, the same here for we added more of the tetrabrom bisphenol here, but the final results with us for us is the same. So as you see here, we can get zinc in the form of zinc bromide released at these temperatures. One thing I forgot to mention, we can stop the treatment at certain temperatures, like below 400 degrees, and take this residue and mix it with water, and these all bromides will be soluble in water. So you don't have to vaporize these metals, okay. And luckily, iron at this temperature, like 300 to 400 degrees, will be in the form of oxides and will not dissolve. So we selectively separate zinc and lead from this dust. What's remaining? I will finish in a minute. What's remaining is iron mixed with carbonaceous material, and you can send it back to the electric arc furnace for recovering of iron and using the carbonaceous material. Now, coming to my conclusion, we did this analysis using the fact stage, and several conclusions were found that we can recover 100% of zinc and lead from the electric arc furnace dust when we use more than 40% of tetrabrom bisphenol mixed with the dust. Under oxidative conditions, 100% of lead and zinc recovery were achieved at lower temperature with no iron content, and the washing process was found to be essential to make the products more pure and improve the pyrolysis or the thermal treatment conditions. Thank you for listening, and sorry for being longer than planned. I finished my presentation, and I'm looking for any questions you have. Thank you very much once again.